here we go. So this is the second half of your notes. We're going to be first starting with the Earth's structure. So one of the things that we did not get a chance to talk about was the actual structure of the Earth. So with that, when we look at the structure of the Earth, we have different sections that it's broken down into. On top, we have that crust, and on top of that would be the lithosphere. So kind of the interaction between that top layer crust and then below the surface. You're going to have your granite and basaltic rocks that kind of make up your lithosphere and the top layer of that crust. Okay, it's obviously very rigid. When we get to the asthenosphere and the mesosphere under the Earth, so we're going to be looking at more of the plasticity regions. So it's not necessarily all liquid-like, but it's going to be more, let's say, fluid as far as how that goes. So the top layers of the crust and the lithosphere actually kind of sit and float on top of the asthenosphere and the mesosphere, especially the asthenosphere. The asthenosphere is going to have mainly those silicate materials. Okay, so that's what's going to cause it to be more that not necessarily fluid-like, but that more plastic-like component. Okay, so then as part of the mantle, you're also going to have that mesosphere. It's more rigid below that because of the pressure, the high pressure. Okay, and then as we get further down, you're going to see the layer of the outer core. Okay, the outer core is going to be more of a liquid, but it's made up of more heavier elements like iron, nickel, maybe some gold, lead, those type of things. And then as we get down even further, we talked about this before, this is kind of what sets up the Earth's magnetism. This will be the inner core, and that's going to be solid. So solid iron, solid nickel. Okay, and again, that's because of the great pressure that we see as we go further down. Alright, so yesterday we talked about this a little bit, but here are your three types of boundaries, so make sure you draw these, just a quick little diagram for each, and understand what's going on at each type of boundary. So the three types of plate boundaries, remember these are where the plates actually interact on Earth, so those tectonic plates. Divergent boundary would be when we see those plates being pushed apart, so we're getting new crust made, that divergent boundary. Convergent boundary is where they're actually coming towards one another. This is where we're going to see possible subduction zones, and in that diagram there you can see the one diving, the one plate diving under the other one. Usually that happens when we have an oceanic plate, which is more dense than a continental plate, and it's going to dive underneath, and that's where crust is going to be destroyed, okay, kind of recycled. There we can see volcanoes occurring on the other side of that continental plate. Okay. For transform boundary, this is like we talked about with the San Andreas Fault. Those plates are actually just sliding past one another. Again, there might be areas where they kind of get caught. When they get caught and they slip, okay, that's where we're going to see an earthquake that would occur. Okay, so transform, sliding past, no crust is either destroyed nor created at these types of plate boundaries. Okay. Again, here's a little rundown on divergent plate boundary. Again, the most common that we see would be in the oceans, where we see these ocean ridges forming, okay, pushing out that new rock as it cools from the magma coming up to the surface, and that's going to cause those plates to pull apart. If you look at the Atlantic Ridge, you can see where it runs through Iceland at the top, and on land when we see these occurring, it's not going to be considered a ridge anymore. It's what we call a rift valley. So that's what's going to be created when we see this happening on land. Okay. And here it is. Here's Iceland. You can see, literally, you can see that area where those plates are being pushed apart. So you can see how the landscape has been changed because of it. You can literally see that rift valley running through the country of Iceland. So we call that rifting or continental rifting. The rift valleys you can see in Iceland. Okay, and here's a little diagram of it where we see the fault lines running through, and we're going to see on these fault lines, like we talked about yesterday, if we look at this picture, we can see those fault lines, we can see the tectonic plate boundary, and we can also see where a new ocean basin is actually has been created between the African plate and the Arabian plate, where those are actually being pushed apart. So when we see a rift valley forming on land, like we have in Iceland, at some point, as those get pulled further and further apart, we get new crust being made, and water starts to fill in, we can create a new ocean basin, and eventually, like you see there with the Red Sea, eventually we could have a whole new ocean created like the Atlantic. Okay. And then here's another diagram to kind of show that. So here we have, the two tectonic plates being pushed apart. We have continental crust sitting on top of the lithosphere, that Rift Valley at first. Then we have that, a sea that would be forming. And then as it gets further and further apart, as that continental crust gets further and further apart and starts to fill in with the ocean water, we could have an even bigger body of water, which would be a mature ocean. Okay. All right, so here's our 4 stages of plate formation: magma upwelling. Okay, ocean plate formation. So from continental plates splitting apart, we have that magma coming up through the crack in the rock between the 2 plates. We have a Rift Valley that's created. An example that was given in the picture, the East African Rift Valley. New ocean basin, example would be the Red Sea. And then we have that mature ocean when they get further and further apart. And obviously that ocean water fills in, or water fills in, we get the example of the Atlantic Ocean. That's how the Atlantic Ocean was actually created, when those continental plates were pushed apart, okay, in development. Now we're looking at the other. So we have the 3 types of convergent boundaries. So with divergent boundaries, just one type. There's different features associated with the divergent boundary. When we talk about convergent plate boundaries, we actually have 3 different types. So we have continental. So when 2 continental plates come together and are interacting with one another. We have oceanic continental, when we have an oceanic plate interacting with a continental plate. And then we have oceanic. So that would be 2 oceanic plates coming into contact with one another, converging towards each other. So when we look at those diagrams, you can see A is talking about oceanic continental. So we can see how that oceanic plate is going to be the one that subducts underneath the continental plate, because that continental plate made of granite rock is going to be more buoyant than the basaltic oceanic plate. If you look at the continental in the diagram labeled C, you can see that. I know the faces cover it up, but if you look at that one, we're going to have what's called folded mountain ranges that occur, because we're going to see those two plates, because of the same buoyancy, they're going to create those folded mountains like the Himalayas. When the Indian plate actually ran into the Eurasian plate, you can see on the other one, oceanic. We're still going to have some subduction going on, but you're going to get islands or volcanic islands that are created due to that subduction zones, or those subduction zones. That's one way that we're going to see islands in the ocean being formed, is through oceanic convergence. Okay, so here's another rundown. Here's continental. Continental crusts, like I said, less dense, very thick. Plates collide and mountain ranges form. Again, those would be called your folded mountains. Okay, and usually these are very steep mountain ranges, like the Himalayas, like the Alps, like parts of the Rockies. Okay, because of the destruction, because of what is happening with these 2 plates, because of how that granite rock is actually made and how less buoyant it is. Okay. Continental convergent plate produced the Himalayan mountains. So here's a rundown. The Asian plate met with the India plate, and like I said yesterday in the video, those mountains are actually still growing today. We could have some volcanism, as you can see in parts of it, so there might be some subduction, and when we see that, we are going to have maybe possibility for some volcanic mountains to form as well in different parts. Okay. We also, if you look off into the ocean, you can see where that ocean ridge is out in the Indian Ocean, where those plates are being pushed apart, and then when they come in contact with other less buoyant plates like the continental crust of Asia, then we're going to have those new mountain ranges being formed. Okay, so you kind of put it all together. There's a divergent boundary out in the ocean. Here's a convergent boundary on land that was created. Okay, oceanic continental crust is still less dense, very thick. Oceanic, thinner, very dense. So a lot less buoyant. So the more dense something is, the less buoyant it is. So as it's going to sit lower in that asthenosphere, and so it's going to be the one that subducts below the continental crust. And this is going to form a trench. Again, when we see that crust subducting into the mantle, we could have what's called a volcanic arc being created. Example of that would be the Cascade Range. Okay. I'll throw a nice little diagram. Make sure you guys are drawing these diagrams, because they're very helpful. For me, when I was going through and looking at this stuff the other night, as a refresher, just looking at the picture really shows a lot. And you can see where the trenches form. You can see how the one plate subducts under the other, and we can see that volcanic mountain range, that volcanic arc, and how it's actually created. So this is kind of going back to last week's targets as well. This is one way that we see those mountains being formed, is through subduction of that plate and those volcanic mountain ranges or volcanic arcs being formed on land. Okay, so that's oceanic continental. Main thing, remember, the oceanic crust, because it's less dense, because it's less buoyant, or sorry, more dense, less buoyant, it's going to be the one that subducts underneath the continental crust. Okay, here's another example of that. So Mount St. Helens is actually a volcano that was created because of a subduction zone. And you can see that whole Cascade Mountain range that runs from Northern California up through Washington is all part of a subduction zone. And there's actually a lot of volcanoes that are found that are still active, still quite active in that range. Mount Shasta up near Mount Shasta, California, that is a volcanic mountain, erupted quite a long time ago, but is still, I think they've actually considered that one dormant. Mount St. Helens, still considered active. Same thing with Mount Rainier, okay? Because we're still seeing movement of those plates and subduction of those plates underneath that continental crust plate, North American plate, okay? All right, oceanic. Again, so that oceanic crust is made of basalt rock. It's a lot more dense than your granite rock. The older, cooler, more dense plate subducts below the younger, less dense plate, and we could form a trench. So we could still have subduction zones going on. The younger the plate is, the less dense it's going to be. The older it is, the more dense it's going to be. So it's going to subduct under that younger one. The oceanic plate will melt, the one that subducts, and will form what's called a volcanic island arc in the middle of the ocean. Okay. Some examples: Japan Island, the Aleutian Islands off the coast of Alaska would be a really good example of a volcanic set of islands that were made in this way. Okay, and here's another little diagram. Again, make sure you're drawing these. So here's your two oceanic crusts. We can see where the subduction zone occurs. We have that trench being formed out in the ocean, and then on the other side, further away, we're going to see those islands that are formed because of that crust being melted and magma welling up and creating new volcanoes. So everywhere along that, all along that whole boundary, it's a possibility to see these new islands being made. Okay, and that's why we see these kind of islands that are formed along the way. Okay, all across that boundary. Again, so the last one, we talked about this at the beginning, but here's your transform boundaries. So when we look at this, we're seeing interactions that occur between different plates, okay, where they're actually sliding past one another. A lot of times we see these happening out in the ocean, but they can also occur on land. The main example of a transform boundary would be your San Andreas Fault. Okay, and they're actually just sliding past. So crust is neither created nor destroyed at a transform boundary. Okay, and you can see in the diagram that movement is pushing past one another. Again, where they get caught up and then slip or pull real quick past one another, that's when we have energy being released, and that's what creates those major earthquakes. So a major thing that you need to write down as far as an event that happens at these transform boundaries is going to be major earthquakes. Okay, so here's, again, they're sliding past one another. A fault is produced, which is basically a crack in the earth, and an example would be San Andreas Fault. So a major crack in the earth that runs pretty much from San Francisco all the way down through LA. And so different parts of this fault may get caught, and when they actually get caught and then finally release, that's when we end up with a major earthquake. And again, we talked about it yesterday a little bit. In parts of Southern California down towards LA, there's a huge chunk of the fault that is that has a huge amount of energy being put on it right now because of the movement of those plates. And at some point, they believe that when that big chunk slips, we're going to have a major earthquake down in LA. Okay, one of your targets asks you to talk about hotspots. So hotspots occur when we have a mantle plume. So it's magma from the mantle. It's super hot. Below the plate produces that magma because it becomes less dense, because it's heated. It's going to rise up. And when this happens, okay, think of it being all this energy, all this heat, all this magma just underneath the surface, and you like have a cork on it, and it's ready to, and it's going to, when it finally gets released, when it breaks through the rock, So we have possibility of a new volcano. Have this super hot magma in this, for whatever reason, this areas get superheated. There's not really a reasoning for why this happens in certain areas, but we have the super hot magma and these big plumes that accumulates over millions of years, and as those plates move over the top of it, we can get the possibility of new volcanoes being formed. So the Hawaiian Islands were formed in this way. That oceanic plate, the Pacific plate, actually moved over this hot spot, and as it was moving further to the north, we got new islands being made along the way through those volcanoes that were created through this hot spot. Okay, so here's a cool little picture. So you can see there's that hot spot. As it heats up, that magma rises. We get new volcanic islands being made as they protrude from out above the ocean. Okay. So the oldest island in this picture would be Kauai, right? Because it's furthest from that hot spot. That had to have been created the longest ago, or had to have been created further back into the past. Okay. So hotspots are stationary, like I said. They have abundant volcanic activity. With that, there's also going to be, an abundance of earthquakes that occur because that ground is moving each time we have an eruption. The lithosphere, or those plates, are going to move over the top, and we create new volcanoes progressively as that plate moves. And here's a little video on Hawaii's hotspot and how those islands were created.
Volcanoes usually occur at plate where the continents collide. When they hit, they release unimaginable energy, punching up molten rock from deep inside the Earth.
The Pacific Ring of Fire marks a whole
series of these plate
It's got half the world's active
volcanoes.
Hawaii is more than 2,000
Hawaii
miles
is more than 2,000 miles from the nearest collision zone.
Beneath the ocean floor is a mysterious area
of super hot liquid rock.
Hot enough to melt a hole through the Pacific
Pacific plate, punching up fresh lava.
It's called a hot spot.
It's called a hot spot.
The ocean floor is creeping
gradually northwest at 3 inches a year.
But the hot spot under
it doesn't move.
A volcanic island builds up, but as it
builds
moves away from the hot spot, it is cut off from the source of lava
and dies.
Over the hot spot, a new volcano forms. But if the big island is growing, then what's happening to the island of Oahu? Oahu should be shield-shaped, but it's not. It's long and thin.
Okay, so it's going to talk about Oahu and how over time it's actually changed shape. But when we see those volcanic islands being formed over that hotspot, we're going to see kind of a shield shape. There were some other processes that took place to create the island of Oahu and what we see today. But just know for our slides that that hotspot stays put, the plate moves over the top of it, and we create new volcanic islands. Okay, we talked about it a little bit yesterday. Here's a little video on Yellowstone. And
recently, scientists have collected new data, giving them a better picture of Yellowstone's underground plumbing. Right beneath the caldera from the last eruption sits the magma chamber. And it's fed by a plume of magma stretching down 465 miles northwest into Montana. It's mostly solid rock with the potential to liquefy. And scientists are closely monitoring it. Magma, or molten rock, is rising through the plume into the magma chamber at 2 inches a year.
There's no reason for it to stop, although it might come in spurts. Our images show wider parts and narrower parts, so it's like slugs of material that are flowing in a sewer line. And this restless Yellowstone caldera is truly living, breathing, and every once in a while it burps.
The danger is if the plume starts liquefying and moving up at a faster rate.
Natural systems can throw us a lot of curveballs. A lot of things can happen that we're not really ready for.
Scientist Jake Lowenstern is looking for a pattern connecting the supervolcano today and its 3 prior major eruptions. 2.1 million years ago, 1.3 million years ago, and 640,000 years ago.
In 2 of the really large eruptions at Yellowstone, so much material comes out, entire mountain ranges end up falling into the ground and essentially disappearing.
One 50-mile stretch of mountains simply disappeared by collapsing into the magma chamber. University of Toronto geologist John Westgate has tracked the ash from Yellowstone's prior eruptions.
It covered much of the United States. It occurs right out of the Pacific Ocean. It's even found in the Gulf of Mexico. Up in northeast Montana, there's a site that we're working on. The tephra is over 7 meters thick. These eruptions are enormous. The amount of material erupted from them, huge.
When Mount St. Helens erupted in May 1980, it blew off one side of the mountain and triggered an avalanche of snow, mud, ash, and rock. Driven by the wind, the ash landed in 11 states and up into Canada. But that's nothing compared to the amount of ash from Yellowstone's last 3 major eruptions. In magnitude and volume, each one was far greater than Mount St. Helens. Today, there's little evidence of the supervolcano's violent past. The 50 by 30 mile caldera from the last eruption was covered by lava and ash and smoothed over by glaciers. Forests now conceal the scars.
Okay, so a little perspective on hotspots. This is a little perspective on how those plates have moved throughout history of Earth. So we look at 250 million years ago, Permian era, we're going to see the Pangea, and you can see how it starts to split apart. Triassic, Jurassic, now we're moving further. Cretaceous, 65 million years ago, and then here's our present day. So you can see the new oceans that are being formed. You can see those giant land masses. This was in your article, talked about Gondwanaland and Laurasia, which are 2 of the major continents that were made after Pangea started to split apart. You can also see how we might have gotten different fossils that could have crossed onto different parts on different continents, and where they ended up is where we see that evidence for continental drift and for plate tectonics. Okay. So if we look at this map, so in 50 million years, we have the continued movement of those plates. You can kind of see where our continents might end up. So if you look, you can see how North America is actually going to be further away from Eurasia. We can see the Eurasian plate. You can see how the Atlantic Ocean is going to get quite bigger. The Pacific Ocean might get somewhat smaller because of that movement. And then we could see in certain areas other continents maybe getting closer to one another. Okay, so pretty interesting how we can see these changes that might occur. Again, we'll be long gone by then, but 50 million years into the future, Earth might look a lot different. And it is, believed that, or proposed, hypothesized, that even further into the future, we could have another giant supercontinent that is made because of the movement of these plates. Okay. So that's all we have for today. Make sure that you write your summaries. I'll have some questions on the board that you need to be able to answer by the time you're done with today's notes. Make sure you have pictures drawn, and then we'll get started with the activity that we're going to do after this. But make sure you write your summaries and add those questions, and make sure you can answer questions along the way. Okay, thank you for watching.